Hello and welcome back. In the past few lectures, we have discussed about the fracture behavior of MMCs under monotonic or static load. But in practical scenarios, it is more likely that an engineering component will encounter dynamic or fluctuating load or stress. Therefore, it is important to understand how materials behave under dynamic loading. So, the failure that occurs under dynamic load is known as fatigue failure. So, before we discuss about the fatigue behavior of MMCs, it will be good to have a general discussion on fatigue.
Fatigue failures occur under the conditions of dynamic or fluctuating stress. So at this point it will be good to know what kind of typical fluctuating stress cycles are generally encountered in engineering components. So when you talk about these load cycles or stress cycles, you may have a completely reversed cycle such as this one in the sinusoidal form. Okay, so here it is first going towards the positive direction to a peak and then coming down and going all the way to the negative direction with the same amplitude. Okay, so when this occurs, this is known as a completely reversed stress. Okay, but it does not necessarily have to be completely reversed. There could be other kinds of fluctuations also. For example, you can have a stress cycle like this. So in stress cycles, you have parameters such as the maximum stress, sigma max, the minimum stress, and the stress range, sigma r, which is equal to sigma max minus sigma minimum. Okay. So a stress cycle like this can be thought of made up of two components mainly, a mean or steady stress sigma m, which is nothing but sigma max plus sigma minimum divided by 2, and an alternating or variable stress sigma a. Okay, and apart from this, as I said before, you also have the stress range sigma r. So in the previous case, when it is completely reversed, sigma minimum and sigma maximum are equal to each other, equal and opposite to each other, and in that case, the mean stress will be 0, right? But as I said, it doesn't have to be always completely reversed. You might have a case like this where sigma max and sigma minimum are not equal to each other. And then you may also have a random stress cycle like this. Okay. And by convention, tensile stress is taken as positive and compressive stress is taken as negative. So the alternating stress is equal to sigma r by 2. Okay. And there is one more parameter that is considered in fatigue, and that is the stress ratio written as R, and it is equal to sigma minimum by sigma maximum. So for a completely reversed stress cycle, R will be equal to -1. Okay. And there is one more parameter called amplitude ratio A, which is given as sigma A by sigma M, and if you write it in terms of R, it will be 1 minus R by 1 plus R. Okay, so these are the different parameters with regard to the fatigue test or the fatigue property. Now let us see how the fatigue data is represented. Okay, so the fatigue property is generally represented as a fatigue life in terms of the number of cycles to failure at a particular stress. So the fatigue data is collected as a function of number of cycles at a particular stress. So this kind of curves which are obtained in this manner are known as the SN curves. That is stress versus number of cycles to failure. And generally the data is collected under completely reversed stress conditions. So as the stress is increased, the number of cycles to failure or complete fracture will decrease. Okay. So this curve would typically look like this. And for many materials like steel and titanium, this curve will become horizontal after a point. Okay. So that particular stress at which it becomes horizontal is known as the fatigue limit of the material. This is also known as endurance limit. But there could be materials where this curve does not become flat, rather it continues to go down. So for materials such as aluminium, magnesium, that is what you will see. The curve goes down progressively as the stress is increased. Okay. So in such materials, there is no well-defined fatigue limit as such, and therefore for such materials, the fatigue life is defined at a particular number of cycles. For example, it could be 10 to the power 8 cycles. Okay. So the fatigue life is given with respect to a particular number of cycles, a high number of cycles such as 10 to the power 8 cycles. So the stress at which the material can go up to 10 to the power 8 cycles, or the stress corresponding to 10 to the power 8 cycles, will be taken as the fatigue strength of the material. Okay, in cases where there is no well-defined fatigue limit. And this curve can be expressed by an equation like this. N and sigma A we have already defined before. P and C are empirical constants. And now if you talk about the fatigue test as to how this kind of curves are generated, the test is generally conducted by subjecting the material first to a high enough stress where failure is expected to occur at a fairly smaller number of cycles, and this stress could be around, for example, 2/3 of the tensile strength. And then the test stress is progressively decreased for the succeeding specimens until at one point the specimen does not fail at that particular stress. Okay. Okay. So this continues till a specimen does not fail at that particular stress, when the stress is low enough. Okay. And when the data is plotted after doing a test in this manner, it will give rise to that SN curve. Okay. So whatever we have discussed so far, it was under the condition of completely reversed stress cycle where R is -1 or sigma m is equal to 0. But practically it is very likely that the stress cycle may not be completely reversed. Okay. So therefore we need to consider how the material will behave when it is subjected to a stress cycle which is not completely reversed. Okay. So let us see that how the fatigue data is represented in that case. So there are several ways of determining the SN curve for a scenario like this where the stress cycle is not completely reversed. For example, it could be the stress at a particular stress ratio. So the stress which could be, for example, the maximum stress can be plotted against log of number of cycles for a fixed value of R. Okay. So let's say R is equal to plus 0.3. And then the same data can be collected at different values of R. For example, R could be 0. Then it could also be negative, such as minus 0.1 or even -1. Okay. So here you can note one thing. As the stress ratio becomes more positive, which is equivalent to increasing the mean stress, the measured fatigue limit increases. Okay, so as you could see from here, the fatigue limit, that is the point at which it becomes horizontal, that increases as the value of R becomes more positive. Okay, the other way of determining the fatigue life in this kind of loading condition where it is not completely reversed is by plotting the alternating stress sigma A against number of cycles or cycles to failure at a fixed value of mean stress. Okay, so let's say this is for sigma m1 and then the mean stress is varied. So here sigma m1 is less than sigma m2, that is less than sigma m3, and that is less than sigma m4. Okay, so here you can note that as the mean stress becomes more positive, the allowable alternating stress decreases. Okay, and there are other ways also to plot this data. For example, the maximum stress versus the cycles to failure at constant mean stress, and maximum load versus cycles at constant minimum stress, for example. Okay, so these are the other ways of plotting the fatigue data when the stress is not completely reversed. Okay, and the other thing that can be noted about fatigue data is the fact that for each mean stress, there is a different value of the limiting range of stress. And this relationship between the mean stress and the stress range can be represented through a plot known as Goodman diagram. Okay, so here if we plot the range of stress along the vertical axis and mean stress along the horizontal axis, then you would get plots like this. Here sigma u is the ultimate tensile strength of the material, and sigma naught is the yield strength. So this plot or this relationship is obtained for a fixed number of cycles or at the fatigue limit of the material. Okay. So you can see that as the mean stress becomes more tensile, the allowable range of stress is decreasing. Okay. Until when it reaches the tensile strength sigma u. Okay, so that's what you see over here as it reaches the point where the stress is equal to the ultimate tensile strength of the material, sigma r becomes 0. Okay, so here this is the alternating stress sigma a, and sigma r of course is the difference between the maximum and minimum. So this is the sigma minimum curve, and this is the sigma max, the upper one, and therefore the difference is the sigma r or the range of stress. The fatigue behavior that we have discussed so far is basically high cycle fatigue, and the data presented are basically from fatigue tests performed under stress controlled conditions. But scenarios are often encountered in which the failure can occur at relatively high stress and low number of cycles. Okay, so such fatigue is known as low cycle fatigue. Okay, so as I said, this occurs at high stress levels. Stresses of thermal origin or thermal stresses can lead to such a scenario. And in these cases, the fatigue occurs not due to cyclic stress, but rather due to cyclic strain. So in order to understand low cycle fatigue, we will have to consider data generated from strain controlled fatigue tests. And if you look at the stress strain curve generated under such conditions, when the strain amplitude is held constant, it will look like this. So here OA is loading in the positive direction or in tension. Now if it is unloaded and reloaded in the opposite direction, that is in compression, then yielding will occur at a lower stress, which is the point B over here. So the lowering of the yield point when deformation in one direction is followed by deformation in the opposite direction is known as Bausinger effect. Now, if it is again reloaded in tension, a hysteresis loop will develop, as you could see from here. Okay. The dimension or width of this hysteresis loop will be given by the strain range delta epsilon. And you can also note that the total strain consists of an elastic strain delta epsilon E and a plastic strain delta epsilon P. Okay. So the total strain delta epsilon T is equal to elastic strain delta epsilon E plus plastic strain delta epsilon P. The material may go cyclic hardening or softening or may remain stable, but ultimately during the deformation process a stage will reach where stable stress strain loops will be developed. Okay. So if you look at this cyclic stress strain curve, that can be found by joining the end points of these stable loops which develop. So these are the developed stress strain loops, and if you join the endpoints, you will get the cyclic stress strain curve. The monotonic stress strain curve is somewhere here. And the cyclic stress strain curve can be defined by this equation, similar to the power equation which defines the plastic flow during monotonic loading. So N prime is known as cyclic strain hardening exponent. Similarly, K prime is the cyclic strength coefficient. And the usual way of presenting the low cycle fatigue data is in terms of these plots between plastic strain range and cycles to failure. This is basically a straight line like this, which is given by this relationship, which is known as Coffin-Manson relation. Here delta epsilon P by 2 is the plastic strain amplitude. 2n is number of strain reversals to failure, wherein one cycle is 2 reversal, and this parameter epsilon prime f is known as the fatigue ductility coefficient, and this is approximately equal to the fracture strain for many metals. Okay, so this is how the low cycle fatigue data is presented.
Alright, let us take a summary before finishing this lecture.
So to summarize, we can say that engineering materials can also experience dynamic loading condition, and under such load or stress, the failure which occurs is known as fatigue, and this generally occurs at a much lower load compared to the yield stress, okay, because this is kind of a cumulative damage which occurs in the material when it is subjected to dynamic loading conditions, and eventually after a certain number of load cycles the material will fail, okay. And then we have defined different types of loading cycles. For example, the completely reversed load or stress where sigma m or the mean stress is 0 and the stress ratio is -1. And we have also discussed about how the fatigue data will look like or how it is represented when it is not completely reversed. So in such cases, we have seen that the fatigue data can be represented by plotting the stress, for example, the maximum stress versus the number of cycles to failure at a fixed R value, okay. And in that case, R is kept constant by applying a series of stress cycles with decreasing maximum stress and adjusting the minimum stress such that it is a constant fraction of the maximum stress, okay. So that's how the R will be kept constant, okay. And then it can be plotted against the number of cycles, and you can get a series of plots as you vary the R, okay. And another common way of plotting such data when the stress is not completely reversed is plotting the alternating stress sigma A versus number of cycles to failure at a constant mean stress, okay. Right, so here also as the mean stress is varied, a series of plot can be obtained, a series of SN curves. And here we have seen that as the mean stress becomes more positive, the allowable alternating stress decreases, okay. And we have also discussed about stress controlled fatigue and strain controlled fatigue. Here, as the name suggests, the stress during the test is kept constant, and here in case of strain control tests, the strain amplitude is held constant, okay. So this one is given by the well-known Baskin equation, and this can be described by the Coffin-Manson relation.
And with that, we come to the end of this lecture, but there is more to come on this topic. Keep watching.